Morning, how are you? Can you hear me? 5271950. I paid something close. I got 526.51 megawatt. But yeah, but if we don't try these things at home, and if we want to be an engineer and power systems engineer, it's going to be very challenging. That's what I can say. So write down. Now I understand that you rounded it. Thank you very much for your answer. I really appreciate it, and it's very close to the answer. It's because of round off. It came like that. So let's go to the first step quickly. I'll go through it quickly. It's not something that we need to do in power systems 1 third year. It's R is given. You write down the value, which is 202.98 ohm. L is given 0.1815 Henry. Frequency is given 60 Hertz. These are the given things. So you can calculate inductive reactance. Lecture. Okay, I'll speak to you. Thank you. Inductive reactance XL is 2 times pi times F times L. And you must tell me what the value you're getting. Write down the answer quickly. Write down the answer. Yes. Please write down the unit. It has a unit ohm. Next step is to calculate impedance. Z is square root of R squared plus L squared. Tell me the value of this one. Not really. Yes, I told you. Only that is going to be approved. So far from it. Students go to talking to this. Oh, goodness. And then you have only from the I'm thinking I'm calling the phone. Okay, thank you. Okay. We did not receive feedback from the registrar office. For submitted. No, but now it's going to be everything issued in an admission letter for next year. So they write to specific agenda. Now, a person to out to specific if they receive anything from the registrar for the students. That's going to be a problem now. Yeah. And Emmanuel, did they give you anything? Yes, okay. So what's the value of 214.2 ohm? Now the next point is that to calculate the power factor. For 5, calculate its value and tell me what's the power factor. Calculate the power factor and let me know. It doesn't take so long. Power factor is R by Z. R over Z. Power factor is R over Z. What's the value of power factor? Please write it down. 0.948. What is sine phi? What is sine phi? You need to know sine phi as well. You know cos phi, you can calculate sine phi. Point 318, which is okay. Now you calculate phase voltage is sine voltage over square root 3. Tell me the phase voltage. Quickly, you can't spend so much of time. $199.18. So that's that voltage, and then you calculate the phase current. Calculate the phase current. I phase current will be phase voltage over Z. Phase voltage over Z. Calculate the phase current and tell me the value of phase current. $929. That's correct. Right, now you calculate phase
MVA, meaning V phase voltage, V phase times I phase. Phase MVA, meaning the MVA per phase. It's the MVA per phase. V phase times I phase value, the per phase MVA. You calculate in mega now. The current and voltages that you showed there, one was in kilovolt, the voltage was in kilovolt, the current you wrote in ampere, but you make sure now that the phase voltage and phase current, when they are multiplied, they are in volt and ampere, then you convert it to mega and tell me the answer. Please write down the answer. Please write down the mega volt ampere for V phase I phase. Quick, it can't be. It's 20 minutes almost. We on a single second year tutorial. 185, that's correct. Now you calculate per phase megawatt. Per phase megawatt is phase MVA times cos phi power factor. Per phase MVA times the cos phi will give you the per phase megawatt. So what is value? It takes 5 seconds to do this calculation. You have per phase MVA, you multiply it by cos phi. How many seconds it takes? Give me the answer quickly. $175, that is correct. That's megawatt unit, and now you calculate per phase megawatt is phase MVA times sin phi. Give me the answer of this per phase megawatt. Again, it should take 3 seconds. It's taking 3 months. What's the answer for surface megabar? Phase MVA times sin phi. You have sin phi already 0.318. Give me the answer quickly. Okay, 58.9. Now you go to the next step. Three-phase megawatt is per phase megawatt times 3. So what's the value? Three-phase megawatt per phase megawatt times 3. Please give me the answer quickly. $526. That's the one that Umeshan wrote in the first place. So thank you very much. If you get that one, and come to the next one is three-phase megavar, which is per phase megavar times 3. What's the value? You must find it, Sahil Laljit, you must find the answer in mega. We didn't write it in mega. We wrote the sentences here is megawatt. So answer should be in megawatt. In your case, in watt. Do you note that? Sahil, you must note that what you wrote there is not in mega, because what we are asking for is the mega. The question asks for mega. Question is not asking for watt or power consumption in general. It's asking for megawatt. So we must write accordingly. Now megawatt per phase MVA, we have it. And we just need to multiply it by 3 now. And what should be the answer? 179. Everyone is getting that? Everyone got that one? Okay, if you got that one, we can go to the next one. This one we are calculating the resistance and inductance is the opposite. Is the opposite of that previous one. The resistance and inductance need to be calculated for an RL load that is connected to a three-phase voltage system with a phase voltage of 199.18 or 19. What you calculated is the same voltage that is given there, and the frequency is 60 Hz. We have to calculate the active power and reactive power. And the active power and reactive power are given here. We have to calculate the resistance inductance. Active power is given as 235.35, and the reactive power, sorry, that's megavar, 85 point, that is megavar. Let me correct this one. Let me just correct this one. This megavar. coming 1 second. You try, if you have tried, you can write down the answer over there. Did you try it? One is 1 home. Okay, we'll correct it. It's not matching with my answer, but we'll correct it. Let me just upload that corrected one. I have added another tutorial on this one, so it will come there as well. Okay, Umeshan is saying something not matching with mine, so we'll verify that one. So what is the first step? To write down what is given. Phase voltage is 99.9 kV. That is given, right? And then frequency is given 60 Hertz. What else is given? Megawatt is given 35.35. Megavar is given 84.56. These are the things that are given, right? There is nothing else given. We have phase voltage 199.19. We have frequency for 60 Hertz. Total active power 235.35 megawatt. Reactive power megawatt 84.56. Let's now go to the next step. We calculate per phase megawatt, which is total megawatt divided by 3. Can you see? It's just the opposite of the previous one. So per phase megawatt is how much? $74.85. That's perfect. So 78.45, and then we can calculate per phase megavar. So it's again total megavar over 3 is just again the same. So what's the per phase megavar? $28.19. That's perfect. Now when we have that, we can calculate our phase MVA, and MVA we can calculate for megawatt and megawatt. Megawatt squared, sorry, it should be square root of megawatt squared plus megavar squared, megawatt squared plus megawatt squared. Then we take the square root of that, and then we get the per phase MVA. So what's the value? Give me the answer. Where is the answer? It doesn't take 3 months. I gave the formula and everything. You just need to calculate that. What's the per phase megavar? Sorry, megavolt ampere, per phase megavolt ampere. How much? We don't have any answer from you. Still waiting. Anyone? Meshan, Sahil, Anelisoe. The formula is written on the screen. You can see. Formula is written on the screen. Megawatt squared plus megawatt squared, and then you take square root of the whole. Root over megawatt squared plus megawatt squared is written on the screen. This is per phase megawatt squared. Yes, and this is also per phase because we're calculating per phase megavar, and the answer is 83.36. That's correct answer. It should not have taken so long, right? When we have this per phase MVA, we can now calculate the power factor cos phi. Phi is megawatt over MVA. Cos phi is megawatt over MVA. It's not R by Z here. It's not applicable here because we don't know R and Z. In the other one, we knew R and Z, so we can calculate. So you can see power factor can be calculated from R and Z. Power factor can be calculated from megawatt and megavolt ampere. So what is the power factor here? And 941. That is correct. Now this is equal to R over Z. You can keep it in mind that this is equal to power factor is equal to R over Z. Now what we have, per phase MVA is 83.36. Per phase MVA was 83.36, and per phase MVA is what? P phase times I phase. Right? Is that okay? Par phase MBA is 83.36 that we calculated, and that is equal to V phase times I phase. And V phase we know 199.19 kilovolt, right? And I phase is V phase over, let me write it again like this formula. V phase remains V phase, I phase is V phase over Z. Is that okay? V phase, I phase. Par phase MVA is 83 point. Calculating MVA is MVA is, I will write it once I'm out of this box. It doesn't allow me to edit, so I'll write that one MVA once again. Once I'm out of this box. So par phase MVA we know is 83.36, and MVA is what? Current and voltage multiplied. So V phase remains V phase, and I phase is V phase over Z. So V phase we know 199.19 times V phase, the second V phase here, we know that 199.19, and Z we don't know. So from this equation, what is Z? What happened to that one? Can you calculate the Z now? This text box, 199.19 times 199.19 over Z. So we need to know now what is Z. That actually is equal to 83.36. So from there we can calculate Z. What is the value of Z? 475. .947, 475.947 ohm. We got Z, right? And in the previous one, look at the screen, we have R over Z is 0.941. We have R over Z is 0.941. So now, as we know Z, we can calculate R. R is 447.94. Right? So now we know R, we know Z. So we can calculate XL is square root of Z squared minus R squared XL is how much? $154. Is that correct? I have 160 or something. Can you verify? No, 653 is not right. 653 is not right. Square root of Z square. 161, it makes sense to me because I have 160.93. 160.93 I have, so it's 161 makes sense. I have 160.93. ohm XL. So when we have XL, we can calculate L. And the screen. Let me write it somewhere else. L is equal to, now you know XL, so it's XL over Y pi F. Yes, 0.4268. That's the correct answer. And its unit is Henry. So that's the one. So R and L are now calculated. And you wanted the formula for MVA. MVA is megawatt squared plus megawatt squared and then square root. Let me just clear everything. MVA is that's MVA, megawatt squared plus megawatt squared, then you take the square root. Is that okay? So Umeshan, you got it right now? Good. So where was it wrong? Yes, that's what I was suspecting. Thank you very much. So when power is given, is total power, meaning is three-phase power. Total power is three-phase power. When we have a three-phase system, when we talk about power consumption, active power or reactive power, we generally refer to three-phase power. So when we have to come to phase, meaning each phase or per phase, we have to divide them by 3, and then only we can go to do the calculation for resistance, inductance, and other things. But one thing you must always remember, everyone, that power factor has nothing to do with per phase or three phase. Power factor is the same. If you calculate the power factor for one phase, it will be the same, given we are assuming that this resistance and inductance that we are considering in these two tutorials are same for all the three phases. They are not different. But if they are different, the power factor for each phase will be different as well. But that's a complete different scenario. Will you remember that in these cases, the power factor for each phase, we didn't talk about that. We talked about per phase power, active power, per phase reactive power, and so on. We did not talk about per phase power factor because that does not make sense. The reason is that the resistance and inductance are same for each and every phase. So the per phase power factor will be the same. I'm coming to the next one, which was not there initially. This is one of the tasks that you will have to try again. You have to calculate the current for each load. It's a small tutorial, but very, very different. It has a lot of learning steps in it. Calculate the current for each load. As you can see, there are 3 generators. One is coming from a 230 kilovolts line and then connected to a transformer, stepping down the voltage from 230 kV to 66 kV. Is the same here on the other side, 230 kilovolt source connected to a transformer, stepping down the voltage to 66 kV. Then is coming. These lines are called bus, BUS. It's not like those bus we take ride to go from one place to other. The bus, electrical bus, where the generator, transmission lines, transformers, equipment are connected to, and from where we take other lines as outgoing. So this bus is connecting to the outgoing feeder of the transformer, and then this is a feeder which has 1 ohm resistance. So for all the other circuit in the C230 and they are connected to the bus via 1 ohm feeder, then a common bus bar, and then there is a grounding connection with 99 ohm resistance. So you have to calculate the current for each load, meaning the current that is flowing through this 1 ohm resistor. The current that is going to flow through this 1 ohm resistor. Is that clear? We will do this. I will solve it. If you cannot, then I will solve it. Not today. Is that clear? You will have to apply all your rules that you learned in second and third year first semester. Thank you very much. So I can go to the next. I want to start the next presentation, next chapter presentation, but okay. Thank you very much. I took 2 minutes more. Now this Sag and Tension is the new chapter. It's a small one, and it's related to the mechanical design of transmission line and systems. But before we go there, I mentioned that I'll always talk about. We'll talk about the tests later on, what we can cover in that chapter as for the syllabus of the test. Okay, so we are going to give this short introduction from the industry or other related aspects with Sag and Tension before we start the chapter. The first thing is that it's related to the transmission of power to the system of transmission. Now, when we talk about transmission of maximum power, it's apparent that everybody thinks, or every engineer or every power system engineer thinks that when you have a transmission line, we are going to transmit maximum amount of power. But it's not like that. One of the most important tasks of electrical engineering is to plan, design, build, or install and operate transmission lines. However, we don't plan and design and install a transmission line always for transmitting maximum power over it. It's a challenging task like any other task that is associated with power system operation, monitoring, control, protection, automation, and everything. And electricity utilities like ESCOM around the globe, including every country and every region, every province where the electric utility is supplying electrical power to the different types of consumers, are developing some sort of mechanisms or infrastructure so that they can deal with the increase in power consumption. And that power consumption is related to power generating stations and related to power consumption taking place at consumer premises. Now, generation takes place at the generating stations and consumption takes place at the consumer premises, be it domestic or be it industrial or agricultural or commercial. Now that power needs to be transmitted. Now as that power needs to be transmitted, we need to talk about the transmission line, installation of transmission line, and those transmission line conductors will carry the power, but not necessarily we always consider maximum power transfer through it. We call it optimum power transfer, meaning as much as possible, but it won't be the maximum power transfer. Now, not only that, we consider that amount of power that will be transferred through the transmission line in an optimum manner, but we also need to ensure that we have a continuity and reliability in power supply, meaning we can supply the power continuously. It does not make sense if we try to supply maximum amount of power to a transmission line and then we fail and end up having no electrical power being supplied to the consumers. And reliability is the other aspect. Reliability is what? Meaning the consumer must get electricity to be supplied as and when they need, meaning the amount and the time. So that is the reliability. So you have to ensure that we supply electrical power to transmission lines in a continuous and reliable manner. The other call during this time is that control. When we're transmitting power, an optimum amount of power to a transmission line, we need to control that. Like consumers are consuming as they need and when they need it. The amount of time is again important. But for that to happen in a continuous and reliable manner, the power systems engineers have to ensure that there are proper controls around each and every parameter, meaning not only the megawatt, the voltage of the transmission line, that voltage that you did in previous tutorial, 345 kV for a three-phase system, the transmission line voltage 400 kV, third transmission line voltage 765 kilovolt is the transmission line voltage. We have to make sure that the transmission line voltage is also appropriate. There are some regulations in each and every country, irrespective of where they are. Those regulations from the country, National Electricity Board or regulatory board, they mention those things. So each and every utility, they have to abide by all those rules and guidelines. Being an electricity supplier or service provider, no one can do whatever they like. They always have to abide by the rules and regulations of that country or the region. Now, when we think of these transmission lines, the amount of power, the voltage at which the transmission line will be operating, the amount of current that the transmission line conductors will be carrying from time to time, and the control and protection operation, there is always a challenge to do so. Apart from that, when we think of installing a transmission line on the ground, it also is challenging task because it depends on the site of installation, meaning where are we going to put those transmission lines. So that's why we see in most of the cases transmission lines are in the outskirts of the city because they are of very high voltage level, like we mentioned, 345 kilovolts, 400 kilovolts, 765 kilovolts, and so on. So we cannot run those high voltage or extra high voltage transmission lines over the city where the city has very, very tall buildings and it's a crowded, populated city because it's dangerous. If something happens, it will kill the people in no time. So we run those transmission lines out by the outskirts of the cities, and from there we go for lower voltage lines like 132 kV. We can also go for 66 kV, and we can also go for 33 kV, 22 kV, 11 kV, and then finally coming to that 400 volt three-phase, from where we can take single-phase supply and three-phase supply as well. But when we run those transmission lines corridor, we call it a corridor, through which the transmission line towers and conductors are installed, they are not always on plain land, meaning sometimes we have to come across rough geography or topology of the plane of the land, meaning sometimes we have small, what you call them, hills, mountains. We have to cover them if we are connecting to utilities from one country to the others, because we find that those mountains are somewhere located at the end of the border or somewhere there. So we have to consider the geography of the land as well. Now, when we come to the next point, which is the reduced losses. When we have transmission line, we always try to minimize the losses that occur in the transmission line due to the resistance present in it. So what can happen in terms of power loss in transmission line is I squared R, meaning it depends on two things. I is the current that is flowing through the conductor from time to time, depending on the megawatt generation and consumption, and the resistance of the conductor. Now, we cannot do anything with the current I, because that is the current that we want the conductor to carry and take it to the consumer premises for their various equipment or the appliances connected to it. And we cannot do much with the resistance R as well, because R will always be there. We cannot minimize it too much. R is rho L over A, resistivity of the conductor material. L is the length. We cannot do much, because if we want to put a transmission line from Cape Town to Drakensberg, the length is fixed. We don't have much control over it. And the cross-sectional area, we can choose a particular cross-sectional area that will make the resistance to be as minimum as possible. But again, if we increase the cross-sectional area, if we remember, that is why we were discussing in Kelvin's economy law, if we increase the cross-sectional area of the conductor too much, then what will happen? Resistance will decrease, power loss will decrease, but the cost of conductor will be too much. And the inter-external depreciation on the cost of conductor will be high, and who will be paying for those costs is the consumers, meaning each and every one of us. So we can do something, but we need to be very careful in terms of trading off while we choosing the conductor cross-sectional area to be too much or too little or too small or an optimum one. So we try to choose optimum conductor cross-sectional area so that the loss is not too much. Also, the conductor cross-sectional area is not going to cost too much of interest and depreciation and increasing the tariff of electricity as well. So that's that part related to the reduced loss. Now, when we talked about these transmission lines that we put in from the generating stations to the stars of the city, and they are most of the cases overhead transmission line. We cannot put them underground. It's very difficult to construct a transmission line system for a long distance like that, thousands of kilometers. So we put them in overhead. But in some cases, we do use underground cables. Sometimes we use, these days it's a very new one that is coming undersea or underwater cables as well. So what we do, those transmission lines are left in outdoors, and they are subjected to atmospheric conditions during the whole of life of their operation. They are subjected to atmospheric conditions, meaning environmental aspects need to be considered. What are the impacts of environmental aspects? It doesn't matter where we install them, even it matters where we install them, because in some cases the line might be close to the ocean and saline water, the droplets will come onto the line conductor, line insulator, line towers, which are metal bodies. Insulators are not metal, like transmission line towers, and the conductors are metal. And those saline water, moisture, fog, that will come onto the transmission line infrastructure. Conductor mainly will get affected. Also, sometimes we might find that there are some pollution if the line is nearer to the highways, like we have highways N3, N2, N4, and N1, and so on. If we run our transmission line corridor along the highways, what happens is in those highways, a lot of high-speed cars travel, and because of that, the carbon particles from the tires of those cars will come and get deposited on the line conductors and insulators as well. Sometimes we might have some transmission lines nearer to agricultural farms as well. What happens from those agricultural farms, they spray some pesticides to make sure that those insects don't damage the crops. So they spray pesticides, and that can come and get deposited on the line conductor, and insulator get infected as well in that process. So it's very challenging task. Even if you think of a desert, that you are running your transmission line corridor in the desert. So what can happen from the desert? There are sands, a lot of sands in the desert. So silicon is going to come and get deposited on the conductive particles, conductive parts of the transmission line system. Apart from that, temperature itself, ambient temperature itself has an impact on the transmission line conductors. For example, we string a line conductor in between two supports. We call them adjacent supports on either side. If you stand in the middle of a transmission line or a distribution line, on either side there will be two supports. We call them adjacent supports. One on the left hand side, one on the right hand side. Those adjacent supports actually support the conductor that is strung in between them. And because of temperature, and the conductor is a metal piece of that particular length, the temperature will affect the length of the conductor, meaning its expansion and contraction will take place as the temperature will increase or decrease, but it will also depend on the coefficient of expansion of that conductor material. If it is a single conductor material, then we call it homogeneous conductor. If we have a number of conductor materials in it to make one conductor, then we call composite conductor. So that composite conductor or homogeneous conductor will depend on the temperature and the coefficient of expansion of those all those materials that we used for construction of them. So expansion and contraction is also a problem that is going to affect. So environment plays a very important role in terms of transmission line conductors planning and design, and that affects a lot in terms of mechanical performance of the system. And as we come to the next bullet point, which is the cost involved. Now, all we do, like we mentioned, we want to transmit as much as power as we want or need. We want to reduce the losses. We don't want the conductor cross-sectional area to be too much because it will increase the cost of conductor, hence the cost of interest and depreciation, hence the tariff of electricity. We have a lot of impacts from environment, no matter where we put them, be it a desert or by the ocean or by highway or in the area where there are a lot of agricultural farms and so on. We need to make sure that we put enough infrastructure and they are strong enough to be working there for the designed period of life, meaning it's maybe 25 or 30 years. So infrastructures must be strong enough. And when we want to make strong enough, we must again consider that how much cost is involved. We don't want to spend too much of money in terms of saving the infrastructure, transmission line infrastructure, meaning the transmission line tower, the insulators, the guards, protective system, etc., earthing system. A lot of things are there involved in the infrastructure. We'll talk about that in the next chapter in detail. So we cannot spend much money, but again, we need to remember one word: we need to be economic, because at the end of the day, all these costs will come to the consumer at the end of the day, and they will have to pay that money for each and every unit they consume every month. Right, now when we come to the next bullet point, which is the electrical performance. Now when we operate these transmission lines for certain amount of megawatt at a particular voltage level from sending end to the receiving end, meaning the end from which the power is sent to the other end, which is called receiving end, meaning where the power is received for subsequent transmission or sub-transmission. Sometimes we use the word sub-transmission as well. I'll come to that word at some other point of time. So we need to look at how the transmission lines are performing in terms of electro parameters. That's why you see the diagram on the screen. It's called a phasor diagram. And you can see there are other quantities that are related to electricity. Mainly, these are the quantities that we always deal with when we talk about electricity and electrical circuits. And the first one is the voltage that you see, that Vs is the sending end voltage. And then you see the other voltage, which is VR, is the receiving end voltage. And you see from the phasor diagram, sending end voltage is larger than the receiving end voltage. The reason is there are voltage drops, and the voltage drops taking place in the conductor because of its resistance, because of its inductance. R and XL, they are causing IR drop and IXL drop. I is the current that is flowing through the conductor, and IR drop and IXL drop gives you a combination which is impedance. R and XL will give us Z, the impedance, we get IZ drop, the voltage drop due to the impedance of the transmission line. So if we subtract the impedance drop from the sending end voltage, we get the receiving end voltage, meaning the receiving end voltage is always going to be equal to the receiving end voltage is going to be less than the sending end voltage, but that is not always the case. Sometimes they might be equal. Receiving end voltage might be larger than sending end voltage. I'll come to that one again. But to go to this current that is shown on the phasor diagram is lagging by the angle phi r, receiving end power factor angle. Phi is the power factor angle and r is for receiving end. So the power factor angle is phi r and current is lagging. Now the question is why this phasor diagram is showing the current to be lagging with respect to the voltage VR. Can anyone answer that? Can anyone answer why is the current lagging behind? Current I is lagging behind the voltage VR by the angle phi r. Why is the current lagging in this phasor diagram? Can anyone answer? Due to it being inductive. That's the correct answer. So it's being inductive load, but it's partially correct. What he's saying, it's not inductive load. The resistance is also there. The resistance is also there. Inductive, we call it inductive load only when there is only inductance present, no resistance. But there is resistance here. There is resistance here. So it's resistive inductive load, it's RL load. We cannot make R to be 0. Even if we take an inductance only, it will have some resistance present in it. Even if we take only an inductor, it will have some resistance in it. So it's RL load. Because of that inductance present, it's not inductive load. We will say that because of the presence of inductance L in the circuit, the power factor is low, the current is lagging. Now, where that inductance is coming from? Where does the inductance come from? We're talking about transmission line, sending end, receiving end. It's a conductor or three-phase conductors that are placed there to carry three-phase power. So where is that inductance coming from? R is the resistance that is coming from the transmission line conductor. R is the resistance that is coming from transmission line conductor that we can calculate using the formula that we know already. R is equal to rho L over A. So can you tell me where is the inductance coming from? Where can it come from? What is the source of that inductance? Any answer? From the generator. There is no generator. We only talking about the transmission line here. We only talking about the transmission line here. Sending end and receiving end is a transmission line conductor. It starts at the sending end and it finishes at the receiving end. That is the transmission line. We're talking about the transmission line. The phasor diagram is only showing the phasor diagram for phasor quantities for the transmission line, sending end to receiving end, nothing else. Generator is at the generating station, not in the transmission line. We don't have generator in the transmission line. Generators are located at the generating stations, power stations. Where can the inductance come from? Anyone? Okay, we'll think about it and ask me tomorrow. Okay, I'm asking another question now. We saw that, or we agreed from the magnetic flux is somehow correct, but we need a lot more discussion on that. Thank you very much. It's a very good answer. That is where we are supposed to go, but we'll discuss that a lot more. But another question I'm giving you to think is that power factor is lagging, right? Am I right? Because the current is lagging, the power factor will be lagging. Is that correct? Do you agree with me? The current is lagging behind the voltage. The power factor, we call it lagging power factor. So we agree that it's lagging power factor. So what other things we can get from power factor? Lagging, and the other word could be leading, right? Power factor could be lagging or leading, and you agree that we have leading power factor as well at some point of time. We can have leading power factor. We can have leading power factor as well. When that leading power factor can happen? When leading power factor can happen? When we have resistive capacitive load. When we have resistive capacitive load. Apart from these two, what can happen? So we can have leading power factor, we can have lagging power factor. What other condition can happen? Unity power factor. When unity power factor can happen? That's correct answer. Thank you, Meshan. When unity power factor condition can be happening? When unity power factor condition, power factor is 1, that's why you call it unity power factor. When we can get a power factor of 1.0. In what condition? What can make the power factor to be 1.0? What can make the power factor to be 1.0? When XL and XC they are same. When XL and XC they are same, does everyone get it? Is everyone okay with that? When XL and XC they are same, we will get power factor to be equal to 1.0. But what happens when lagging power factor is happening? Meaning we have RL load, lagging power. What actually happens? What physical phenomena happens? We just don't do some calculations and then make some conclusion. This is lagging power factor 0.95 or leading power factor 0.92 or power factor is unity 1.0 because XL is equal to XC. What happens when there is RL load causing lagging power factor? What does it mean? What else I will understand or you will understand when you see the power factor is lagging? Okay, just to give you hints, lagging means we agreed that there is some inductance in the circuit, R and L. Is that right? Power factor is lagging means there is some inductance present in the circuit. Now, what does that inductance do to cause the power factor to lag? Because of presence of that inductance, the power factor lags. Because of the presence of inductor or inductance in the circuit, power factor lags. But what actually happens? Yes, it causes the reactive power to increase. It's not like it causes the reactive power to increase. The inductors draw some reactive power. Inductors draw some reactive power. And as you put more and more, you will see the increase. That's again a very good answer. So all those inductors present in the circuit or inductances present in the circuit will cause some reactive power flow, meaning because of the inductance that was mentioned due to the magnetic flux in the transmission line conductors, they cause some reactive power flow, meaning they will be drawing reactive power, meaning someone now will need to supply that reactive power. Now, where that reactive power will come from? Reactive power means megavolt ampere R, MVAR, that we calculated in the previous tutorial, MVAR. Now, as it draws or as it consumes megavar because of inductance present in the circuit, transmission line circuit, who will supply that megavolt ampere R? Who will supply the MVAR? Who will supply that reactive power, or what equipment will supply that reactive power? It will be supplied by either the generators from the generating station. That's the first option. The generators at the generating station can supply that reactive power. But it can be too much, because when you increase reactive power in MVAR, what happens? You use that formula, if you remember that MVA that we calculated in the previous tutorial, what was there? Megawatt was there and megavar was also there. So if we increase the reactive power, megavar there, what will happen? MVA will increase. As the MVA will increase, what we will see? We will see the increase in current. That will cause a lot of loss in the transmission line, lot of power loss because of increase in current. So what we do, if the reactive power is too much, we supply reactive power supplier equipment in the system, meaning we can put some capacitor banks to balance the reactive power from. Now imagine a situation, transmission line is operating at lagging reactive power, meaning it's drawing some reactive power. And the generating station is running at unity power factor. The generators are running at unity power factor. Is that possible? Transmission line, after generating station, what we have? We have the transmission line, and we see transmission lines due to magnetic flux, inductance, and because of the inductance, they will draw some reactive power. So they have lagging reactive power. Is it possible to have a condition that the generators at the generating stations are running at unity power factor? Is it possible? For that transmission line, there is nothing else connected to the generator other than transmission line. No, it's not possible, because they are reactive power. So someone like that's what I mentioned, that if you have a generator and a single transmission line connected to it, it's going to draw some reactive power. The generators need to supply the reactive power, so the generator power factor will immediately become lagging as well, because the transmission lines cannot operate unless it draws some reactive power. You have studied transformers, right? Single phase transformer, three phase transformers. Did you? Yes. If you study three phase transformer, what happens in a transformer? There are primary and secondary, right? Primary voltage, primary winding, primary current, and so on. Then secondary voltage, secondary current, secondary winding, secondary number of turns, and all those. Remember? Do you remember that? Yes. Now what happens? Imagine that the secondary is open. The secondary winding is left open. You supply the voltage, rated voltage at the primary winding of a transformer. What happens after that? What happens when you supply or apply voltage to the primary winding of a transformer? What happens? No answer. What happens when we apply voltage to the primary winding of a transformer and the secondary is left open? Okay, you'll think about it and give me answer later on. Let me go to the last bullet point before I close. We need to look at the electrical performance. Also, we need to look at the mechanical performance of the transmission line. Like I mentioned that we used to string a certain length of a conductor, transmission line conductor, use 100 meter or 200 meter or 300 meters in between two adjacent supports, and those supports can be either concrete pole, steel tower, lattice tower, different names are there. I'll come to those names in the next chapter. So when we string between these two adjacent supports, we need to make sure that they operate for their designed life, and they are always subjected to environmental conditions, ambient temperatures, and those pollution that can come from agriculture farm, highways or desert or by the ocean or anywhere where they are located. Apart from that, there are changes in the length of the conductor due to temperature, and the temperature, like I mentioned, depending on the coefficient of expansion of those conductor materials. Also, those conductors are subjected to wind pressure, meaning we have a lot of storms, wind flowing over the surfaces of those conductors. So they will have to withstand that, because if the wind flows or blows over the conductor surface, what will happen? They start swinging. They will swing, and because of that swing, the conductors can snap from the point of joint or where they are fastened to those structure, meaning to the towers. After certain swings, they will start getting eroded, and at some point of time, they will fall on the ground, meaning there will be no continuity of supply. It will be dangerous, can kill people. There will be no reliability of power supply. Also, in some places, in very difficult situation like cold winter, ice can get deposited on the conductor surface as well. So that will make the conductor even heavier on top of their own weight. So when we design mechanical aspects of a transmission line, we need to consider all these. And when it comes with that, it even comes to the point we need to look at the tensile strength of the conductor material that we are going to use for construction of that conductor. So we go to something now that we learned in applied mechanics or in some other modules. So mechanical performance is going to be considered here. That will cover the mechanical design, but itself is very easy and not much to complicate. But in real life, we have to consider all this. We have to consider how much of power will be transmitted through that line, how much of losses we can afford, what are the environmental impacts, and how much are the infrastructure required, what are the costs involved in various aspects, how this line is going to perform electrically and mechanically. All these, we cannot say, oh, I am putting transmission line, they gave me this task, I'm done. We have to consider each and everything, because if we make this mistake in any of these things, we might find that the transmission line has a very good mechanical performance, but electrically it's very poor. The receiving end voltage is too small as compared to the sending end voltage, meaning we are having a lot of losses here. Resistance is too high or inductance is too high, meaning the design is not good. We have spent a lot of money, meaning it's not good. The reason is that this money is going to come from each and every consumer. It's going to burden them. And as you know that if you increase the cost of electricity, it's like the increase in the cost of petrol or diesel. It will increase the cost of each and everything, starting from the loaf of bread to milk and everything, because all those process industries, they use electricity for processing and storing all the things that we consume or use. So cost of electricity is very important. If we don't consider that, it's a problem. And that is why we need to consider all of this. Does not matter whether we are designing a transmission line for mechanical aspects or electrical aspects, or just thinking about how much power we need to transmit from the sending end to the receiving end. Is that clear? Thank you very much. If you have questions, ask questions.